This diagram shows a standard network switch wired to 4 computers. We have 2 computers for normal users and 2 that act as sensitive servers. Our goal is to separate these 4 machines into 2 completely distinct networks without buying a second switch. By default, a switch treats every port as part of a single group. If one computer sends a broadcast message, we see a ripple effect where that frame hits every single other device connected to the switch. In networking, this is called a broadcast domain. Out of the box, all ports are assigned to this single domain, known as VLAN 1. Grouping everything together creates immediate problems. When employee laptops, secure servers, and even IoT devices share the exact same broadcast domain, every device must process every broadcast frame. This degrades overall network performance. Worse, it exposes sensitive server traffic to any device plugged into a wall jack. To fix this, we have to manipulate the switch's internal logic. We need to build invisible walls inside the hardware itself. We do this by creating virtual local area networks, or VLANs. Look at how the internal logic changes when we apply VLANs. We assign ports 1 and 2 to VLAN 10 for our users, and ports 3 and 4 to VLAN 20 for our servers. Now, when a user computer sends a broadcast frame, the switch consults its MAC address table and stops right here. The frame is only delivered to other ports explicitly assigned to VLAN 10. The servers never even see it. When designing networks, the standard rule is 1 VLAN equals 1 IP subnet. The VLAN isolates traffic at layer 2 using MAC addresses, while the subnet organizes the traffic at layer 3 using IP addresses. The ports connecting our computers to the switch are called access ports. An access port is explicitly configured to carry traffic for exactly one specific VLAN, placing that endpoint device directly into that isolated network. To configure an access port, we access the switch's command line interface. We create the network by typing VLAN 10. Then, we select the interface and type switch port mode access, followed by switch port access VLAN 10. Take a moment to pause the video and practice writing out these exact commands for a new port assigned to a third VLAN for IoT devices. Access ports secure our local traffic perfectly on a single device, but businesses grow. When we add a second switch down the hall to connect more employees and servers, we need a way to maintain these isolated networks across multiple pieces of hardware. Here is our 2-switch topology. If both switches host VLANs 10, 20, and 30, we could run 3 separate Ethernet tables between them, one for each network. That wastes valuable physical ports. Instead, those multiple cables are replaced with a single connection called a trunk. A trunk port is a switch-to-switch connection configured to carry traffic from multiple different VLANs simultaneously across a single wire. To keep the traffic separated on that single wire, the switches use a standard called IEEE 822.1q. Watch the Ethernet frame as it leaves the first computer and hits the trunk port. The sending switch inserts a tag directly into the frame header, identifying it as VLAN 10. The frame crosses the wire, the receiving switch reads the tag, routes it to the correct local port, and strips the tag off before handing it to the final computer. By tagging frames as they leave the switch, we remove the constraints of physical hardware. Logical isolation can now span across an entire campus network over a single fiber or copper link. This diagram shows one exception to the tagging rule. Traffic on the native VLAN, which is VLAN 1 by default, is allowed to cross a trunk port completely untagged. Both switches simply agree that any untagged frame they receive on a trunk belongs to the native VLAN. Even with our switches connected, we still have a strict communication boundary. A layer 2 switch will never forward frames between 2 different VLANs. If a user in VLAN 10 tries to ping a server in VLAN 20, the packet strikes a wall inside the switch hardware. The logic simply drops the request. To establish communication between these isolated groups, we route the traffic at layer 3. We introduce a layer 3 device, like a router or a multi-layer switch. The packet leaves the user's subnet, travels up to the router, crosses the logical boundary, and is routed down into the server subnet. The hardware defaults to total isolation. If a device is in a VLAN, it is secure from outside traffic until an engineer explicitly configures a routing path between the subnets. To verify your configurations, you rely on a few specific commands. This terminal shows the output for Show VLAN Brief. It lists every active VLAN on the switch and shows exactly which access ports are assigned to them, allowing you to quickly spot devices placed in the wrong network. The second terminal shows the Show Interfaces Trunk command. It confirms which ports are actively operating as trunks, lists the VLANs permitted to cross the link, and highlights the native VLAN configuration. Matching that native VLAN across both ends of a trunk is critical. If switch A expects untagged traffic on VLAN 1, but switch B expects it on VLAN 99, traffic leaks between networks. The Cisco Discovery Protocol continuously monitors the link and will aggressively flag your terminal with error messages if it detects a mismatch. Look at this four-part breakdown of our network architecture. We use access ports to connect endpoints, trunk ports to connect switches, 802.1 queue tags to organize the traffic over those trunks, and inner VLAN routing to allow communication between them. By manipulating the internal logic, you turn a single piece of physical hardware into an infinite number of secure, isolated networks.